Artificial intelligence can understand language, recognize images, generate content, write code, and solve complex problems. Yet beneath these capabilities lies something much older: mathematics. AI may work with language, images, sounds, and ideas, but underneath, they are represented and transformed mathematically. In Mathematics in the AI Era, we will explore these mathematical foundations, and the deeper questions AI raises. So, why did mathematics become the language of AI? I can recognize a face, understand a question, generate an image, or write a program. It can feel almost magical. But there is no hidden human mind inside the machine. Behind these capabilities are mathematical operations working on enormous amounts of information. The intelligence we see at the surface has a deeply mathematical structure underneath. When we interact with AI, we see words, images, sounds, and answers. But the machine sees mathematical representations. Images become numbers. Language becomes numerical patterns. Sound becomes mathematical signals. Once information is represented mathematically, machines can manipulate it, compare it, and learn from it. The real world is enormously complex, so computers need a representation of reality. Cameras, microphones, and sensors convert reality into measurable information, and ultimately, numbers. This transformation is one of the foundations of modern AI. A photograph looks like an image to us. To a computer, it is a structured collection of numbers. Pixels encode intensity and color, creating a mathematical representation that AI can process to identify shapes, objects, faces, and patterns. Machine vision begins with mathematics beneath the picture. Language is more challenging because words carry meaning and context. AI converts language into numerical representations, allowing algorithms to capture relationships between words and concepts. Behind generative AI lies a mathematical world of vectors, dimensions, distances, and relationships. The same principle extends beyond images and language. Sound becomes waveforms. Video becomes numerical representations. Sensor measurements become data. Different forms of information can therefore enter the same computational world. The world of mathematics. Numbers alone are not enough. AI needs structure. Vectors represent objects and concepts. Matrices transform information. Geometry describes relationships. Probability captures uncertainty. AI therefore uses mathematical structures to represent information and its relationships. Modern AI draws from several branches of mathematics. Linear algebra provides vectors and matrices. Calculus describes change. Probability and statistics handle uncertainty. Optimization finds better solutions. Together with geometry, information theory, and graph theory, they form much of the mathematical language of AI. Representation is only the beginning. The real question is, how does a machine learn? A model makes a prediction. We compare it with the expected result and measure the error. Then the model adjusts its internal parameters and tries again. So learning becomes a mathematical cycle. And that leads directly to optimization. Much of machine learning can be understood as an optimization problem. A model makes a prediction. A loss function measures how wrong it is. Mathematics then tells the model how its parameters should change to reduce that loss. Through repeated updates, the model moves toward better solutions. In this sense, learning is optimization. The mathematics of AI is not new. What changed was the environment around it. We gained enormous amounts of digital data, vastly greater computing power, better algorithms, scalable cloud infrastructure, and powerful open-source ecosystems. These developments converged, and when mathematics met data and computation at massive scale, AI accelerated dramatically. We can think of modern AI through three pillars. Mathematics provides the structure. Data provides the examples from which patterns can be learned. Computation provides the power to process those patterns at scale. Individually, each is powerful. Together, they create the foundation for modern AI. Now the larger chain becomes visible. Information is represented mathematically, transformed through mathematical operations, and used to learn patterns. Those patterns enable inference, prediction, and decision-making. This is how abstract mathematics becomes practical intelligence. Mathematics is the bridge. And now we arrive at a deeper question. Can intelligence itself be described mathematically? Mathematics can model perception, learning, prediction, and decision-making, but what about consciousness, meaning, emotion, or self-awareness? Perhaps mathematics cannot fully define intelligence, but it gives us a powerful tool to understand it. We have only opened the door. From here, we will explore the mathematics shaping the AI era, from vectors and matrices to probability, optimization, information theory, complexity, and causality. And eventually, we will ask, what can mathematics tell us about intelligence itself? Because the mathematics behind AI is more than equations, it is a way of understanding information, learning, uncertainty, and intelligence. This is a journey into the mathematical foundations of an increasingly intelligent world. Welcome to Mathematics in the AI Era.